And thank you guys for being here, especially 8 o'clock in the morning. It's quite a challenge, I think, getting up at this time. But also thanks to the MD Expo staff for the opportunity to be here again. And just over the last number of years, this is probably some of the best, most cost-effective continuing education you can really give yourself coming to these programs. And I've come to actually believe, not only from the educational perspective, but especially years ago when we were going through all the COVID stuff, coming to these programs almost seems to have an element of psychological therapeutic value to it. I mean, being around like-minded buds, it just kind of re-energizes, recharges your batteries in a sense, and I think it actually reaffirms and revalidates the incredible importance of the work you guys are doing every day. So after you come back from these things, more often than not, I think you're pretty amped and juiced and ready to go again, you know, for at least a week or two before you get beat up again and, you know, bloody. So, but anyway, what I'd like to do is just share some of the stuff that we've learned over the last 20, 25 years or so regarding patient safety, forensic engineering, and the investigation of adverse events associated with medical devices, and the things that we've learned from this really pivotal story book, you know, that really started our entire patient safety movement to Err as Human, came out in 1999, which really was quite literally gave birth to our patient safety initiatives in many ways. And one of the key findings from that book that I found so incredibly kind of boggling at the time was that the errors that we were seeing back then and continue to see are by the systems, the inherent complexity in our environment. I think, and I'm ashamed to admit it, but back in the day, I was in healthcare like you guys for 20 some years. My first conclusion was that the user. They didn't know what they were doing, stupid, and that wasn't the case at all. Obviously, we work with some very bright people, but the complexity of the environments that we're putting our clinicians into are what making things so incredibly difficult to work within. Since then, because we have done a lot more, there's been a tremendous amount of really good work going on. We've got a number of books, papers, specific journals related to patient safety. We're able to track things in ways that we hadn't done before. So we've learned a lot about what we can and should do, but we still have some really horrific numbers going on. Some of the most current best estimates of accidental deaths in our nation hospitals are pushing 400,000 a year. This is consistently, and it's been up there with the third leading cause of death in our country. It's not at all uncommon. You'll find a lot, especially in the healthcare, the caregivers, they can't believe this. It's such an obscene, offensive thought and a concept that their environment is killing over 1,000 people a day, that it just can't be right. And admittedly, the numbers are kind of all over the place because we've got natural deaths commingled in with these accidental deaths. So it's not as much of the absolute number, but the inherent nature of the problem that is what the issue is. And clearly, of these, you know, 400,000 a year, we don't know really how many are due to technology in our equipment, but there increasingly has been a lot of the harm and the adverse events associated with our technology, just because of its inherent and increasing complexity associated with our devices. Fortunately, we have a tremendous amount of some really good resources out there. Were any of you guys able to get the Henry Stankiewicz's presentation yesterday? Yeah, from the VA. This is probably one of the best go-to documents that I've found and I've used over the years out there from the VA on their incident investigation guidebook. Henry was one of the co-authors of this book, and there's just a lot of really good, juicy take-home things from there. ECR, of course, Mark Bruley back in the days. I mean, he was one of the early pioneers doing these investigations and putting the findings of those investigations out into the community. So a lot of really good resources out there that we have available to us that is definitely worth considering. Every engineering discipline that we have, electrical, biomedical, chemical, software, computer science, they all have a subspecialty group associated with them, associated with forensic engineering. And this is really just the investigation of adverse events, you know, why buildings fall down, why planes crash, like why shuttles blow up when they come in on landing. So it's this investigative branch of science and engineering that we also can borrow heavily from. There's a tremendous amount of literature out there in the forensic engineering space about how to best do this kind of work as well. Okay, from our HTM hospital perspective, some of the takeaways, and you might be in some facilities that are already doing this or trying to do this, but what some of the things that we've learned over the last 20 some years is that within the hospital environment, investigating these adverse events is optimally, and this is kind of almost a pie in the sky for some places, ideally done from a team perspective. And preferably at the leadership of that team, head of the team is your risk management people. They often have overall responsibility for these incidents. They may even have attorneys or legal resources available with them. So they often are the best ones to administer the team, but clearly we have to have a place at that table just because of the technology, your patient safety, your facilities people. There can be real subtle things just with the inherent design of a hospital. Transitions, elevator thresholds, sizes of doorways that can contribute to harm, and of course nursing leadership. Why these things are kind of optimal, and again, this gets to be some kind of a pie in the sky thing, but where it has been done and it is working, it works well, because when you have different disciplines coming together like this, everybody, just from our inherent training, we see things differently. The same object, the same pointer, depending on the angle that you might be looking at it, you see something different, whether you see it from the edge, the back, the side, the front, and every one of these different disciplines comes at anything from a different viewpoint. They see it at a different angle. And that gives power to the analysis and helps complete the overall investigation. That's kind of the ideal. The reality, however, these different backgrounds can create some real conflict. It's not at all uncommon that you might get nursing leadership get real defensive, real protective of their staff. You know, even if you imply that a person may have screwed up, they can get defensive. We'll get defensive if they start to challenge our technology or blame our processes. So it can create some serious communication issues, but the benefits can be well worth it if you can get through that. And the obvious reason why we investigate the accident. I mean, this is kind of a real no-brainer. The ultimate goal is to find out why it happened and then do something to prevent reoccurrence. I mean, it's kind of real straightforward. That's not the rocket science overall goal. And it's precisely the same thing that the NTSB, National Transportation Safety Board, does with their airplane crashes. And it's precisely why aviation is one of the more safest forms of travel, because of these people out there literally within hours going through the wreckage and bringing multiple experts from multiple disciplines. You got avionics guys coming in, power plant engineers coming in, you got the medical examiners literally going through bodies, psychologists doing psychological autopsies on pilots and the crew, and all of that information, ultimately, it might take them months, years to complete, but once they do, they publish this stuff and we learn from it. And this is, again, why aviation is quite literally, I believe, decades ahead of healthcare in terms of overall safety, because of the public outpouring of this information. Many of us have done forensic consulting work. Every single case that we've worked on, you had to sign a non-disclosure agreement. I'm going to talk about some of these at the end, cases at the end, but every single one, you don't talk about it. You can't share anything. You're not supposed to do anything about it. And as a result, we have not learned. So I've gone off the reservation a little bit in that regard at the end here. I'm not going to name names or get into the details, but the lessons learned from these tragedies we have to talk about. I don't know if you came across John Nance. He's an aviation correspondent for ABC News. He's a pilot and also an attorney. He wrote an incredibly little book, I don't know, 15 years ago maybe, on why hospitals should fly. And he makes a whole number of comparisons and analogies from aviation, what aviation has done to what hospitals could and should do in terms of trying to prevent accidents and improve overall safety. Really really eye-opening kind of a read. Okay, and fortunately, you know, despite some of the bad press the VA hospitals and system has gotten over the years, they started a National Center for Patient Safety in '99. So they're a system that basically adopted, you know, they adopted many of these kind of processes and techniques from aviation. And it worked kind of really well for them. I don't know if you recall, this was maybe 15, 20, I can't remember, years ago. There was a VA system somewhere in the country that had they were having a lot of cross-contamination with endoscopes or colonoscopes or something going on, and they couldn't figure out what was going on. And so they did exactly what the FAA did. They just grounded all endoscopic colonoscopy procedures until they figured it out. and it worked. They found out what the root cause was and they fixed it. But trying to do that in a private conventional hospital, shutting down a surgical procedure, probably never happened. But it was that kind of approach and mindset towards safety that it is and definitely has worked. And it's, again, it's kind of a no-brainer. And you might be in facilities that you've got a program going, and the kinds of things we've seen in those places where it works, the injuries, deaths go down, interruptions in care, use error, anxiety. One of the things, if you've been on some of these suits, I've been on a number of them, when you bring a caregiver in, a nurse or a doc, and they get deposed, and even worse, if they get up, goes to trial, they'll often get destroyed and shredded. I mean, they just will get every shotgun coming at them. We had a nurse in our nursing program, a critical care nurse, really sharp, experienced nurse, got called in on a drug overdose thing, totally unrelated to her work, but she was so damaged by that. Her confidence in giving medication was destroyed. She had to leave. She came in, she just couldn't function anymore, just because of the process that she got dragged through. And of course, the improvements, outcome satisfaction, all this kind of stuff is just a byproduct of a culture of safety, not just lip service, but a real true culture. And we got a number of different perspectives. So depending on your backgrounds and your viewpoint, your approach to patient safety is all kind of the same. We ultimately all want the same kinds of things, except when we get to the legal side of things. Sometimes they can be competing interests there where, the inherent nature of our legal system is very adversarial, and they got to advocate for the client. And if that means going against learning why something happened, they're going to advocate for the client and not the knowledge. Okay, so just fundamentally from an ethical perspective, engineering and in all of our learned professions, we have ethical mandates for safety. We have to be consciously and ever mindful that of whatever we do, we cannot do harm. We have to make sure that things are done properly and correctly, because society expects that of us, as do the courts. Because if you've gone through a learned profession, we're supposed to know better. So we don't get the slack if you do something that's just naturally going to be stupid and unsafe. Well, if you've been taught otherwise, you're supposed to know better. Like, I can't remember her name, when you know better, you do better kind of thing. We have an obligation. And so as do the clinicians, the Hippocratic Oath, first do no harm. Even Florence Nightingale, the founder of modern nursing over 100+ years ago, had some insight that, very first thing, hospitals shouldn't do the sick no harm. She'd be kind of flipping out right around now if she knew all that was going on in our environments. Regulatory, we have, and you guys are probably painfully aware of this too, we've got a whole number of laws out there, requirements that hospitals as well as manufacturers have to report incidents, whether they even know if they truly happened or not, but anything then involved in the potential injury, death has to be reported for obvious reasons. And we've got the MedWatch forms, and this is precisely also one of the reasons why risk management in your facilities is often the best one to administer and manage and submit these forms. It's generally not recommended that we HTM clinical engineering go off independently putting these forms out into the space, because how these are filled out, the information that's included on them is really, really important that it be done correctly. Not just to cover your ass kind of perspective from the hospital's perspective, but they have to be filled out properly. And that's why the risk people are often the good ones to help do that. There's also, and this is just coming out, CMS is going to be issuing some new safety guidelines starting in 2025 next year. They call these structural safety measures. And that might encourage some places to get a little bit more mindful and serious about how they're doing their safety, internal safety programs. But again, the CMS is it's about time, after 25 years, to try to add some more encouragement and incentives for hospitals to get more mindful of these things. But that might start to elevate some of the awareness maybe a little bit more. ECRI just recently came out very strongly in support of these new CMS measures as well. Okay, one of the realities, however, despite the reporting requirements, despite federal law, this was a report from the Inspector General's office, I think in 2012, that basically concluded that about 86% of the adverse events weren't even being reported. And because of, they didn't know what to report, but also just plain fear of getting sued, getting reprimanded. So a lot of what's going on in our environments just doesn't get reported. And this is one of the other reasons I'm convinced why the horrific numbers of accidental deaths is kind of still staying under the radar. Is like, well, you know, if you died and you were in the hospital, you must have been sick. You know, the fact that we accidentally punched you out, we're not going to know about that kind of stuff. So, but from a scientific and engineering perspective, this is just obscene to me that we've lost this opportunity. It's like a double insult. Not only did we do harm, obviously, to the patient and the families probably in some respect, but we didn't learn anything from it. So it's like it's a double insult when this kind of stuff goes unreported. And this is where, from an engineering and the scientific perspective, this is where we best learn. I don't know if you guys have heard of Henry Petrosky. I think he was a civil engineer, and he still might be with Duke, but he's written a number of really good books on forensic engineering. He's obviously coming in from a civil engineering perspective. I know Vincent had some issues with civil engineers. We had a little talk about that a while back, but he comes at it from, you know, more of a conventional facilities construction infrastructure perspective, but the messages are still exactly the same. You know, we don't want the failures, but you don't want to let a good crisis go to waste, meaning that you want to extract as much possible knowledge and insight from these tragedies as you possibly can. And when you think about it in engineering, and I pump this into the kids all the time, the students, is that the only time we really learn something is when we blow something up. I used to purposely have a lab in a fundamental circuits class where I'd take a resistor, you know, a quarter watt, a half watt resistor, and I purposely would violate V squared over R. I just, you know, and just burn the shit out of the thing intentionally to cause it where it would start to turn brown and then smoke and stink. And I you know, come on around here and take a snort of that. I want to smell that burnt carbon. You know, there is inherent diagnostic value in that stink. If you smell something like that, warning, warning. You know, you're violating the mother laws here. You're expecting that component to dissipate more power than it's designed to do. But when things fail is when we learn stuff. Okay. To do the forensic stuff though in any of these environments takes often a different kind of reasoning ability. And this is where it can be somewhat of a challenge because we're not often trained to be from the deductive side of things. In deductive reasoning, and this is what is required for any forensic investigation, is that we basically start at the result or the observation, the event, the adverse event, the injury or the harm or the death. How did that happen? That's what you start out with. And often the next step is to come up with some preliminary, but also it should be a very cautious hypothesis or idea on what you think may have happened. And sometimes it's often good to not even tell anybody what you think it is. Okay? It's just because to tentatively, temporarily entertain what you think might have happened. The real next step then is to just go and gather as much evidence as you can. And this is why we sequester the devices, the wrappers out of the garbage can, you photograph, you document everything. You gather as much information as you possibly can. You talk to the staff when they'll talk to you. Sometimes they just simply cannot. If they've been involved in a real horrific event, I'll get to it in a little bit, they can't. It's like PTSD or like they just come out of Afghanistan with, you know, walking through minefields. They just simply cannot talk about it yet. And so we have to be mindful of the psychological stuff that they're going through. But you put all this together, you can come up with some conclusions and hopefully the root cause of what actually happened. If you get lucky and you have to take it to the next level, if there's a way that you can replicate the findings, I mean, not to the point where you're going to obviously injure or kill somebody all over again, but if you can replicate things, you then have a way of adding some additional layer of credibility and proof to your conclusions. That's a deductive approach. Many of us, though, in technical, scientific, engineering education, we kind of get trained in just the opposite way, more inductive. We start out learning theory, having lab reports where you got to do Ohm's law stuff, you know, with a LED and a resistor, you know, verifying that all these things kind of work, and you know, to verify the theory. And then if we do this kind of stuff really well, like Ohm's law, you know, where you've got incredibly stable, repeatable things, now you have a law, and then you get a Nobel Prize. But this is the general order in which we kind of were brought up. So to do some of the forensic stuff, we kind of got to tip this whole way of thinking upside down and start a little different. That takes a little bit of doing for some of us. But our environments, you guys know better than anybody else, and the ergonomics people, the non-healthcare people out there have basically categorized us as high risk, high tech, very complex systems within systems. NICUs, neonatal ICU, that's the baby. These kind of environments is what puts what we call a tremendous cognitive burden on the clinicians. They're not trained to deal with all of this techie shit. This is not how they think. This is not their fundamental calling. But they've got to get mindful of all of this stuff, just caring for the patient. Again, unlike aviation, this is where some of the John Nance stuff comes from. There's virtually no standardization in our environments, right? You can go to any one of your critical care units in any one of your hospitals, and they're all different. Maybe the only thing that might be close to standardization is the head wall where the gases are, But every square foot around a patient's bed, I don't know, let's stick a balloon pump there, let's stick a ventilator, So everything is all over the place. So that kind of lack of standardization invites mistakes. This is this subtle kinds of stuff where clinicians might make a mistake and they don't even know they made one, let alone being able to back out of it once they did it. Okay? But from this systems perspective, and this was a kind of a mindset that evolved in my head over the years, that and it took me years and years and years before I could adopt what I read somewhere they called the sterile perspective. Going into every incident investigation as neutral and as unbiased as you can. Because again, I'm ashamed to admit, what did you do now? How did you screw up? I was in this blaming assumption mode that the nurse, the doc, somebody just didn't know what they were doing. And I just didn't know any better at the time. But since then, and what we try to teach from the engineering perspective is looking at this from the systems viewpoint. Not just our machines, which are all near and dear to us and we know intimately, but how do these machines and the humans interact at this thing we call the interface? How does this whole combination work in an environment with lighting, noise? The alarm fatigue issue? This is a big deal. I mean, patients have died because they've crashed and the alarms are going off, alarms are going off. It's like your screaming kid. The parents, you don't even hear the kid, right? After a while, you just tune it out. Everybody around you is hearing the kid, but you tune it out. And humans are no different. You got a multiple Mallory Sana alerts all going off. Okay. The brain just chunks a bunch of that out. But lighting, the facilities, all of this kind of stuff, if your CT scanner is 2 blocks away from the ED department and you're wheeling head trauma patients down elevators, and so facility stuff like that can contribute to these systems issues. We know this better than anybody else as well. Nowhere else but in healthcare do the patients literally become one with the technology. This is not a figurative thing. No place else do we make deliberate electrical connections to the patient's body, low impedance electrical connections, invasive cannulas and arteries, ventilators in the airway. Guy's not going to the bathroom anytime soon, right? So he's probably got a Foley catheter in him. Some of these Foleys actually have thermistors in them. We can monitor bladder temperature. Why not? Pretty much every orifice, we can stick something in there. And if we run out of holes, we'll just cut down and make another one and stick more stuff in it. But that adds a tremendous complexity to this interface thing, right? Because again, it's quite literally, they are one with the machines. And you think about it, our equipment, as good and sophisticated as it is really trying to talk to us through its waveforms, flashing lights, alarms, different alarm sounds, frequencies, intensities, colored lights. The machine is talking to us. The clinician, the user, obviously has to communicate back through touch screens, controls, knobs, dials, knobology, I call it, and interact appropriately. And of course, very like anywhere else, we often have patients in this loop. We've got a really complicated dynamic thing going on here. A lot of things can go screwy, which it does. And you guys, where, you know, docs, nurses, bright, intelligent people, they can just get so, you know, $10,000 box. I don't care. You know, you've seen docs, surgeons throw stuff in the OR, and you can understand their frustration. You got somebody's chest laid wide open. You cannot have an ESU just quit working on you, you know? And so they get understandably frustrated. And I've come to actually believe one of the reasons we get so, you know, at your remotes, your laptops, is I kind of think the equipment is mocking us, you know, when it doesn't work the way we expect. You dummy, you don't know what you do, you stupid. Well, I'll show you. There was a guy, this is in Wisconsin, I was about 15, 20 years ago now. His lawnmower wouldn't start. He went in the house and got his shotgun. He came out, he just blew the shit out of his lawnmower with the shotgun right in the center, just because you know, of course you can't do that, you know, a normal human being, but the frustration, it comes from our, in fact, this has gotten so big, the Milwaukee School of Engineering, this is like 5+ years ago or more, maybe even 10. We have a whole bachelor's degree program in user experience. It's all about human factors and what's going on with that interface. We've got a lot of bright, you know, software engineers, computer scientists, EEs, biomed guys. We can make these great boxes, but we're often clueless as hell about the human being that has to interact with the box. Okay. So how do these things happen? This was another metaphorical model that I used to always bring into any new investigation, and this is developed by James Reason. He's like an experimental psychologist out of the UK, came up with this, and you've all seen this at some point in time, I think, the Swiss cheese model of accident causation. And I tweaked it a little bit to fit our healthcare environment. But fundamentally, what the model gives us a way of, again, looking at our environment is that we've got all these intrinsic hazards out there just because of the nature of our environment. And how do we prevent those hazards from doing harm? Well, we set up barriers. Okay? So we have administrative policies and procedures where we hire hopefully appropriately trained people. We don't make them work 48 hours, you know, 2 days straight. You have administrative things in place. Your facilities are optimally designed so that, you know, a bed and 25 infusion pumps and a balloon pump can all fit in the elevator at the same time, kind of stuff. Our equipment, we hope, is optimally designed. And of course, the last off in line of defense is our user. But this model, the Swiss cheese, implies that these little holes in this cheese are they're not perfect. The barriers are not perfect. And when you get this magical alignment of the stars here in this case, these inherent threats have a clear shot, bam, to do harm. I've also come to think about this in my own head of these holes being like lava lamps. They're dynamic. They're not fixed in one position or a specific size, but they can change, you know, daily depending on what's going on. So it adds a whole lot more randomness and complexity to how we hurt people. Okay, and Reason also has two kinds of failures he refers to. In fact, these holes he refers to as being of two different kind of natures. One due to what we call active failures, what we typically think of as a conventional use related failure, where it often blames the user. And oftentimes when we follow that approach, or you've identified a user and you blame the user, the whole investigation tends to stop at that point. We think, hey, we solved the problem, we fixed it, we're okay, you know, we're smart, we've got it down. But he tries to encourage us to think about the latent conditions. And I really like that term he used called resident pathogens. These are the bad guys, the latent hidden things within our environments, within our systems that we don't even know are there. And that often don't show themselves until we have a catastrophic event, a failure. Shuttle goes down, plane blows up, bridges collapse. Well, how did that happen? Well, you've got some little bolt or something that wasn't designed right, it rusted out, it did something, but it's these resident pathogens that if we can be more proactive and be on the lookout for those things, we can identify them before they create the real harm. Okay, so, and then lastly, the competing and could be complementary is from the legal perspective, and this drives a lot of what we do or often don't do in our environments just because of fear of what might happen to us legally. And if there are suits involved, typically, and if a patient is injured or killed and there is a suit involved, typically this is the scenario. They're often going to bring in the manufacturer. Whoever has the biggest pockets often is going to get brought into the suit, regardless of how they may be related or not. But the hospital are on one side, the patient plaintiff is on the other side, and it's a very binary, very adversarial kind of a boxing match that is now going to ensue. And this is also another reason why risk management is often a good overall, in charge of our efforts, because they're into all of this kind of stuff. And depending on how our findings are documented, how things are written up, it may come back to hurt or help you, depending on how you simply word your findings. In every defense case that I've worked on, every single one, I think except one, I was instructed right from the start, do not write anything down. Do whatever you guys do, check out your stuff, but then call me. Because anything that I would ultimately write down ultimately becomes discoverable on both sides. Everything you guys, every work order, PM thing you put, anything you put into your CMMSs is discoverable in a lawsuit. If you have an attorney on one side or the other side that is astute enough to know that you have a treasure trove of potentially useful or very damning information in your own environment, they have access to that stuff. They have every right to all that stuff. They can even ask for every email that you may have tried to generate or may have generate. So the discovery is a big part. Evidence, obviously, they can even come back later on after they've dug through all of your CMMSs and found out, only half of your ventilators are being inspected when you say you're going to inspect them. And they can ask for more detail through these interrogatories approaches. Okay? The other thing to be incredibly mindful about, especially in our area, is this concept of spoliation of evidence. This is something that we could accidentally do, and not even know that we did it. And there is some slack if that should be the case, if you just accidentally destroyed some evidence. But on the other hand, it can be very, very bad for your defense if you have done that without you knowing it. I did a taser case a long time ago in Wisconsin where a young guy was killed, and I found a device online that I could interrogate the taser. It was basically an app. You plug it into the USB port on the taser, and it would download a complete time and date stamp, firing history, time, date, even had a temperature sensor in the taser. It measured that. So I went through this whole download, got all the data, doing multiple firings with the thing, which was illegal in Wisconsin to have a taser at the time. I had a special court order from a judge in Waukesha in Wisconsin to have the taser, but the battery went dead on me. And I could not buy stuff for tasers from Wisconsin just because it wasn't, they couldn't sell it to anybody in Wisconsin. I had a buddy in Omaha. I found a spare battery pack, a third-party battery pack in Nevada. I had him send it to my buddy in Omaha. My buddy in Omaha sent me the battery pack. I'd gotten through all of my testing, had all the data downloaded from the taser. I plugged the new battery pack in. Taser didn't work. The battery was a third-party battery, and I was clueless, but there was firmware in the battery. This is how the taser kept itself current. So you buy a legitimate battery pack from the company, you upload it, it uploads. The thing detected this third-party battery, shut the taser down. If this thing never had gone to court, but if it had gone to court, I would have been ripe to have been sued for malpractice. Except blew out the evidence. The evidence was all gone, and that's what spoliation is all about. I was traumatized after that, and then many years later, I got involved in a case, ventilator-related death. A toddler had some multiple congenital birth defects, and he was sent home on a ventilator. And he was, I don't know home how long he was home at, but evidently what had happened, they had a home health care agency respiratory tech come in, evidently do some adjustments. The tech supposedly left. Some hours later, the family said they didn't hear the ventilator making noise anymore. No alarms went off. They went to check on their baby. Baby's dead. Okay. And so they were going to come after the home health agency and the ventilator manufacturer. And the attorney that I got involved with, he wanted me to basically check out the ventilator to see, was there anything wrong with this machine? Was there a potential case there? Okay, so the deductive procedure like that. So I didn't know anything, first of all, how to do any of that. But fortunately, I was able to find an exemplar, the exact same model number of the ventilator involved in the case. So I did all of my testing, initial testing on the exemplar. You never, never, ever want to go at working on the actual device, especially if you're at all unfamiliar with it. But I knew these devices had a event log embedded in the machine. You know, they time and date stamp everything. You turn it on, turn it off. Every alarm that goes off is time and date stamped, and that's all embedded in the machine. It was a bitch, though, to get it out. I couldn't call the company and say, hey, you might be a co-defendant in a lawsuit. You want to tell me how I can check your machine out? They're not going to tell you any of that. Fortunately, the old Biomed bulletin board, you remember that? We used to have a bulletin board some years, a long time ago. It was for biomeds, and I just put an inquiry out there. Anybody have some procedures on how I can download the event log? And one of our good dudes sent me the procedure, and it was even a real funky, like an RJ6. It was a real bizarre serial cable that I needed to go from the ventilator into an old DOS hyper terminal kind of thing. It was a real ugly muck to download all of that information. We eventually got it out, and I had to parse it all up and clean it all up. And ultimately, what I was able to show in the internal clock and date stamp was still right on. Basically, what it revealed is that the event lost power at 12:23, and this particular code, it was unplugged from the wall. You know, pulling the plug. But this device had its own internal battery, so of course it just kept running. A minute later, the ventilator was shut off. Okay? 911 wasn't called until a couple hours later. So what this strongly suggested, someone in the family disconnected the ventilator on the kid. Attorney saw that, he ran the other way. This was a potential homicide now, you want nothing to do with it, and he left. But it's getting that data out of the machine. The point is that you have to make sure that when you, in the process of downloading these event logs, is that you don't erase them. Okay? Less than a year or so later, a totally different part of the country, totally different case, another puzzling infant death happened. I did the exact same thing, which I could do really quick now because I knew how. I downloaded the event log, and what it shows here at 1:13, the machine was turned off, and it was turned back on again at 5:08. And this was one of the defense cases where the lawyer said, just call me up and tell me. And so I told him that, and he goes, yeah, so? I said, so who's breathing for the kid? You're not going to bag a kid for 4 hours. And the baby ultimately died like around 7 o'clock later. So they turned it off, turned it back on, turned it off, and the baby didn't die, kept living. You know, so they turned. So another case that went awry that way. Okay, this was a case I talked about a number of times before. This was at the last hospital I was at. Patient went into cardiac arrest in the middle of the night. CV patient, he had heart surgery the day before, went into cardiovascular ICU. Middle of the night, he went into cardiac arrest. They went to defibrillate him. Ball of flame engulfed this patient's head and neck. Not a spark, ball of flame. At first, second-degree burns all over his head and neck. You could see the intensity of the fire. Endotrache tubes, stopcocks. He had a swan line, pulmonary artery wedge, a catheter in his neck. Burnt that. You could see the charring on the paddle. And needless to say, this freaks the shit out. I mean, you just don't blow up people in the ICU. Right? And so this freaked people out. Literally the morning, I'm getting a call, and I'm getting ripped. What is wrong with you people? Your defibrillator just blew up a patient. They instantly assumed, instant conclusion, the defibrillator was faulty. This never happened before. You're responsible for the defibrillators, therefore you're faulty. You know, and I'm going, whoa, 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 back the bus up a little bit, you know. I mean, they were freaking out. And so we did everything we normally do. We went and got the defib out of service. We recorded everything. We took pictures of the bed, everything. We recorded everything. And of course, understand, right after that, I went down trying to talk to the staff. They're not talking to me. Like I mentioned before, they were so traumatized, and I didn't understand this at the time. I regret to admit that, but I didn't understand the extent of the trauma that they were feeling, because I just kept going down there and bugging them, and they get out of here. You know, I'm just covering my ass. They wouldn't talk to me, but little by little by little, this was all coming together, because of course, risk management, our insurance carriers, how did you do this? You know, they don't want this going out into the world. And it was literally an upside down jigsaw puzzle. I had no preconceived ideas. All I knew was, going in, starting, how do you blow up somebody? Well, you got to have oxygen, ignition source, and a fuel. That's kind of all I kind of knew. I remember Apollo 1, when the astronauts blew up, but that's about all I had. But little by little, we had all of the information together, and what I was able to reconstruct with a Resusci Annie is that, first of all, this patient was a real big barrel-chested dude. He went into cardiac arrest, and the first thing nurses do, they'll lower the bed so they can, facilitate chest compression. Well, they lowered the bed, but it wasn't down all the way. We had evidence of that. The nurse that went to defibrillate the guy, relatively short-statured nurse. Wasn't her fault, but she wasn't able to make good paddle contact here. These older Lown defibrillators, this is an old HP at the time, old Lown defibrillators, peak open circuit voltage 5,000 to 7,000 volts, not uncommon. Also, the patient had a ventilator, endotrach tube in. They disconnect the ventilator and they just put the hose next to his neck. But see FiO2 on the blender, close to 100% O2, flooding the head and neck with pure oxygen. He had a swan line in, big 4x4 gauze on his neck. They went to discharge, incomplete paddle contact, an arc. So that's what I effectively put back together. And the first thing they want to do is blame the nurse, but this is classic James Reason Swiss cheese. It's just the alignment of these stars here that created the problem. Infusion pumps. You guys have probably seen, these are probably the most ubiquitous devices we have. We, thousands of pumps. Every hospital, just thousands of pumps. And, not at all uncommon for really critically ill patients to have multiple pumps on them at one time. And in this particular case, this is like a 30-month-old little toddler, went in for heart surgery, went to the pediatric ICU, and they had all these different pumps on him. And he kind of stabilized, so the doc said, let's stop the epinephrine. And they we're going to start an IV of packed red cells. Nurse came back about a half hour later, epi bag gone. The whole bag gone. Overdose, overinfused the patient. And I don't know if this little, I think this is going to work here. Yeah, you can kind of see this. I just got some colored fluid. Free flow, if you've seen this before, not normal IV, supposed to be kind of normal, but under a free flow condition, you can be up to 700-800 mLs. I mean, it's just, and you free flow something like epinephrine, incredibly powerful vasoactive. I mean, you just, and the infant didn't die, but he went into cardiac arrest and was permanently brain damaged as a result of that. Well, the hospital's argument, I got pulled in by the manufacturer of the pump to find out, is there anything about our pump that could have caused this to go on? And the hospital was adamant that this pump had a history of broken door rollers, and that's why this thing happened. And so that was their position, their defense. And my eyes started coming out thinking, well, would this pump even run with this door roller not being there? So I went out and I got actually 2 or 3 of these right off of eBay. The company, of course, was going to give me pumps. I said, I don't want your pumps. I don't want any. I have to defend that you might have, reinforced them or did something to improve them. I'm going to get them on my own. I got them on my own. Took them apart, went through inside out and backwards, and ended up being incredibly impressed with just the level of design and detail in terms of safety mechanisms and procedures built into this pump. They used the disposable cassette that the pump, when it was properly used, the door was properly closed, would engage these solenoid pins that would control the flow of the fluid through the pump. Okay, incredibly good. When I also did some testing on the pump itself, it had a real sweet little feature that on the cassette, they had a little valve on here that the nurses could use to prime the pump. So it worked like a little needle valve. You could set a flow with a little needle valve, or you could pull it open. It only took a fraction of an inch here, 1/10 of an inch or so to be fully open. So it was very convenient for the nurses to prime the pump. Very good design. Okay? But when you put the cassette in the pump took control of that valve. I have a little micrograph here, if this will work. You can see how that pawl comes out, opens up the valve. Now the pump has control. When you turn it off and you pull the cassette out, that valve gets shut. Okay? So when the cassette is properly mated to the pump, pump has control. You take it out, now you have control. Okay? And I thought, well, how many ways can you break a door roller? And I thought, well, so I put a cassette in. If the cassette wasn't properly seated, you know, and you had some bulwark come along, well, you know, I'm going to close the door. And to close the door, you had to push down on that little lever. And I thought, well, what does that take to break this pump? Just a force gauge. Who's going to do that? You get that kind of resistance, 30 some pounds of resistance. You know, most astute users are going to say, something's not right. This shouldn't be that hard to close that door. Okay, so fundamentally, what I end up finding out though, that even with the door was broke, and this was just pure accident, it was just a pure accident, that if I held the door closed with just the right amount of force for just the right amount of time, so if I had 3 to 7 pounds of force, if it was less than 3, I get an alarm. If it was more than 7, I get an alarm. And I had to keep it closed for just a few seconds while the pump ran through its self-test. The pump would start and run with a broken door roller. It would actually run, but you had to go through that precise and exact scenario in order to make that happen. And the point I made is, how likely is that? Because the pump was working fine in the OR. Patient came up from the OR to the PICU, same pump. So someone in the OR would have had to have done that if it was broke. Someone in the PICU would have done that. And of course, ultimately what I concluded is that there's nothing wrong with the pump, but in the process of switching the epi out to the packed red cells, that valve got moved. And unfortunately, and this is kind of nursing 101, the IV line wasn't clamped off before it was removed. And that's what ultimately caused it. But again, this poor nurse was just understandably just wrecked. Another one, quick case, laparoscopic cholecystectomy. If any of you had gallbladders or appendicitis or any kind of endoscopic procedures done, I mean, it's incredibly great procedures in terms of recovery and outcomes for the most part. But in this case, a young guy, a middle-aged guy, went in for a gallbladder, and about a week later, died, collapsed in his bathroom. And he actually had gone back to the ED because he was claiming stomach pain. And ultimately, what found out that these laparoscopic instruments, they typically cold sterilize them and like glutaraldehyde, and repeated cold sterilization has been shown to degrade the isolation. So it was either capacitive coupling or insulation breakdown that caused these stray ESU currents, burned a hole right through his stomach. So he died of massive peritonitis as a result of that. What was really disturbing, on that same crash cart, the same cart that the ESU was on, they had a device that behaves almost like a ground fault circuit interrupter. If it senses stray ESU currents, it shuts the machine down. They had it right on the cart, but they didn't use it. And if they had used it, that type of injury would have been prevented. So the CS people, and I don't know how many places are doing this, but one of the papers I came across, it was pushing like 15 to 20% of the laparoscopic instruments that were tested had failures in the insulation, just from this repeated cold sterilization. Okay. And a quick last thing here. This is a case involving a contrast injector. 60-some-year-old guy went in for just a routine angiogram, and after they did the angiogram, you know, imaging the coronaries, with one use of the machine, they pulled a catheter out and they put it in the ventricle to evaluate the ventricle, so you can look at stroke volume and see how good the heart is. Well, the nurse or the cath lab tech responsible for filling the injector got called out of the room, came back in when they were ready to do the ventriculogram, and they saw that the syringe was in its downward position. You know, these injectors, they won't work unless the head's down in a downward position. The plunger was retracted. Thought, yeah, well, somebody filled it for me, because the contrast agent's a clear syrupy fluid, you know. And so the doc said inject, they hit the button, no contrast, all air, 100 mLs or so of air right into the guy's ventricle. And where does it go from the ventricle? Right up to the brain. I mean, they killed him. The doc went, you know, understandably berserk trying to pull the air out, and it just was way too late. And but this is a classic human factors kind of a thing. the human came in, everything looked ready to go. You can't quite tell, is there water in there or clear fluid? I mean, it looks like it's all ready to go. But this is just and in some of these labs, they're almost like an assembly line process. There's a lot of urgency to keep things moving. And it's precisely that urgency. This company had an air emboli detector that could have fit right on the end of the syringe that would have prevented the machine being using it, but it was an option. And that freaked me right out. And I got kind of blasted by their attorneys because my point was, why is it an option? This is the last line of defense for these people, and you made it an option. It's like giving you one brake on your car instead of 4. Well, you want 3 more brakes, that's an option. But anyway, the whole point of this, all of these things from the last 25 years is look at every one of these incidents, no matter how traumatic they are, as a precious learning opportunity, but also a moral and ethical obligation. Again, not just to the injured patient and the family, but not learning and finding out what happened. It's a double insult if we don't learn what happened. So find out what those failures were. Don't just manage the last error, because that's where we tend to attach the blame. And then when we do that, we just kind of stop because we think we've figured it out when we really maybe didn't. Okay. And so like Henry Ford, the only mistake when we don't learn something. Okay? So, all right, I think we got it right on time. Make some sense? It's fun working in hospital, but you don't want to be a patient in one, do you? That's okay. Yeah. Okay, well, thanks again for being here, and I hope you have a good rest of the day, all right? Thank you.